In this section, we are going to talk about count regression models. Specifically, we are going to talk about the Poisson regression model, we are going to talk about a quasi-Poisson regression model, and we are going to talk about the negative binomial regression model. Now, the last two models you can use in the case of over-dispersion. What this means, I will get to later. Okay? Now, let us first look at the Poisson distribution and its properties. Okay? So the Poisson distribution can be written as follows, where we have y as the random variable and k would be the outcome of interest. And so the Poisson distribution is written as Euler's number to the power of negative lambda times lambda to the power of k divided by k factorial. And note that the distribution depends on one parameter, and that parameter is lambda. Now, the important aspect of the Poisson distribution is that lambda is equal to the mean of the data, and it is also equal to the variance. Okay? So let me give you an example here. Suppose that you are a little shop owner and on average you have 7 customers per day. Assume that you have collected data over multiple days and on average you had 7 customers. Okay? Now, if you are interested in the probability to have exactly 5 customers in your store, or that 5 customers visit you on a given day in the store, then you would calculate the probability as follows. You take Euler's number to the power of -7, right? Because on average you have 7 customers in the store, times 7 to the power of 5 divided by 5 factorial. Okay? And that will give you the probability that exactly 5 customers show up on a given day. Now note that you can use the data or you can use a Poisson distribution if the mean is equal to the variance. Okay? Now, very often you have the case where the variance is actually larger than the mean. In this case, you have over-dispersion. Now, if you have over-dispersion in your data, then you should not be using the Poisson regression model, but you should be using one or the other. Okay? Let us implement the 3 models, the Poisson regression model, the quasi-Poisson regression model, and the negative binomial regression model in R. The three packages which we need for now are called PSCL, AER, and MAS. Make sure that you have installed those packages on your computer and that you have also activated those packages. The dataset which we are going to work with right now is called HHPub and is a dataset associated with the National Household Travel Survey from 2017. And we are interested in the vehicle count by household and which factors influence the vehicle count by household. First, we are going to subset the data to eliminate all missing values in the variables of interest. So let us call this new dataset HHPub data, and we are going to use the command subset to subset the original dataset. And in particular, we are interested in the household family income. And note that those are coded from 1 to 11. And what those codes mean, I will come to soon. And then we are also interested in the home ownership of the family. This is called home own. And we are also interested in whether they live in an urban or rural environment. And of course, the last variable of interest is the vehicle count. So this is HH vehicle count. And note that this goes from 0 to 12. Okay, so households have either 0 vehicles or they have all the way up to 12 vehicles. Okay. Now note that the income is coded from 1 to 11, but that the spacing in terms of dollar amounts isn't equal. So we have to make sure that we associate a dollar amount to those numbers, okay, such that we are getting the correct estimates. Now, when you look at the codebook associated with the NHTS, okay, then you can see that, and I'm taking now the averages between the brackets. And so at the lower end, we have $10,000 of annual income. Then we have $12,500 and so on. All the way up to $200,000. Okay. Now, we are also creating the name which is in here, and this is simply from 1 to 11. And then we can create this new data frame, which we call income. And in there we have the code of the family income and the income itself. So now when you look, you can see that where you have, for example, the 7 and the 8, that corresponds to an income of $82,500 and $112,500. Okay, and note that those are household incomes. Next, we are going to merge our newly created data set. Okay, this, of course, we are going to use the command merge. And now we see that when we have an income code of 1, that corresponds to $10,000 of income. Okay. Now, note that the home ownership and also the urban and rural environment is strangely coded as 1 and 0. Okay. Actually, here there was a typo. Let's just make sure everything is running smoothly. Then we would like to have this though as a dummy variable that is easily that you can easily interpret. Okay, so for that purpose, we are going to create a new data set, a new column, which we call a rural, and this means that if the person lives in a rural environment, and this is simply the urban rural -1. And note that this actually is coming from the description of the data. So it is often very important that you look at the code book of the data, and that tells you how the variables are coded. Okay. So now we have created our dummy variables. Now, before we implement the Poisson regression model, we should look at whether the data suffers from over-dispersion, where the variance is bigger than the mean. And let us first do it a very simple test. Let's just say you're just looking at the mean of the vehicle count. And that mean is 1.98. So on average, households have about 2 cars. And note that the variance for the same variable, that the variance is 1.38. Okay, meaning that they are actually very close together. So let us now run our first Poisson model. And to do this, we are going to write b hat Poisson. This is simply the name of the output object, how I want to call it. And we have to use the function GLM, generalized linear model. And the variable of interest is the household vehicle count. And we'll make this as a function of income, whether they are renting a place and whether they live in an urban or rural environment. And the data is, of course, HHPub data. And now note that we have to say the family is equal to Poisson. Then we summarize the data. And now we have the following results. Okay. So first of all, note that income and rural are positive and significant. What this means is that if your income goes up, that also increases the number of cars you have. Also, if you live in an rural environment, then that increases the number of cars as well. If you're renting a place, that this actually decreases the number of cars you own. Note that all variables are statistically significant. Now, the package AER, which we have loaded before, this package here, it actually has a function which is called dispersion test. And that function allows us to conduct a hypothesis test whether the data suffers from, or the model suffers from over-dispersion or not. And here we simply have to enter the object, which we have created here. And then we hit enter. And what we can see is that the p-value is very high. And as with any other hypothesis test, we fail if the p-value is above 5 or 10%, then we fail to reject the hypothesis, the null hypothesis. So here there's the indication that there is no overdispersion in the data. So this example illustrates the use of the Poisson regression model. Now next, let us move on to two additional count regression models, the quasi-Poisson regression model and the negative binomial regression model. And the data which we are going to use to illustrate both of those models comes from the following article, which is called Black Lives Matter: Evidence that Police-Caused Death Predict Protest Activity. Okay. Now note that in this article you have what is called supplementary material, which also includes the data set and explanations to replicate the results found in the model or in the paper. Note the data set that we are going to use is called BLM, which is slightly modified from the original data set, okay, where it has the data is, you have the geography, you have the total number of protests, you have the population of the city, you have the population density, you have the percent black in the city, you have the black poverty rate, the percent of bachelors, or the percent of the population holding a bachelor, the college enrollment per capita, the share of Democratic voters, the death per capita overall, police-related, and the death of black people per capita related to police. Okay, so that is the data which we are going to use for this example. Now, the variable of interest, or the outcome of interest, is the count of protests in a particular city. Okay? And we start by calculating the mean. So mean BLM total protests. And we see that on average the protest we have 0.5. Note that in the data there are actually a lot of zeros. Okay. Also, let's calculate the variance. And we can see that the variance is significantly higher than the mean. Okay. And remember that using the Poisson regression model means that the mean is equal to the variance. Okay, so here we already have an indication that this is actually in reality not the case. Okay, again, an indication but not a certainty. Very soon we are going to use the dispersion test once we are estimating the Poisson regression model. Now, to cut down on the typing of formulas, I am going to store the formulas in 3 objects. What we are going to do, and this corresponds to the first 3 models which are presented in the original publication. Okay, I am going to write EQN1 is equal, and then I am simply going to write the formula which you usually, this part here, which you would usually write in the model. Okay, so this, I hope this will cut down on the typing. So the first model, we are going to use the total protests as the dependent variable, and then the independent variable is the log of the population plus the log of the population density plus percent black, the black poverty rate, then the black poverty rate squared, plus the percent bachelor, plus the college enrollment, the per capita college enrollment, and the demographic share. Okay. So now we have this object here which has the equation. Okay. A note for a second model, we are going to use the very similar explanatory variables or independent variables. But in addition, we are going to use we are going to add the death, the Black Death overall, the Black Death per capita. And in a third model, we are going to see the overall death per capita. And note that those deaths are always caused by police. Okay, so we will call this equation 1, 2, and 3. Okay, so now in the first step, we are going to use we are going to estimate the Poisson model. Let us estimate first a Poisson regression model. So we are typing b hat, let's call it model 1, or b hat 1 is equal to GLM. And now note that I just have to type in EQ1, which is the equation 1. And the data is called BLM. And the family is Poisson. Note that we have here a bachelor. This is of course written differently. There we go. And so now we can say summary, b hat 1. And we get the first results from this Poisson regression model. So note that here we do not have any variables that are describing police death, but we can see that if there is a higher population, then we have more protests. Okay. Also, if the percent black and the black poverty rate are higher, then that also leads to more protest activity. Okay. And the same is true for if you have those educational variables as well as the share of Democrats. Now let us conduct the dispersion test for this model. So we type in simply dispersion test b hat 1. And note that here the p-value is relatively small. So we would not reject the null hypothesis of what is called equidispersion at the 5% level, but we would reject the null hypothesis at the 10% level, meaning that the model probably suffers from over-dispersion. Okay? Now, in order to estimate the count regression model when we have over-dispersion, what we can do is we can estimate a quasi-Poisson model. To do so, we type in b hat 2 equals GLM. We are still using equation 1. We are still using the BLM data, but now we are using a quasi-Poisson model. And then we do summary b hat 2. And now note that with the quasi-Poisson model, that the population density is not statistically significant anymore. Note that, and this is also mentioned in the notes, that the coefficient estimates have not changed, okay, compared to the regular Poisson model, but that the values, the z values, or the standard errors are different. Okay? Basically, what the difference is between the model is that in the Poisson regression model, you can see that here it is called the dispersion parameter is taken to be 1, meaning there's mean and variance is the same. Whereas in quasi-Poisson models, dispersion parameter is actually estimated as well in the model. Okay. Now, in the final part, what we are going to do is we are going to estimate negative binomial models. Note that in the original article from which this data is taken, that the authors are estimating a negative binomial model. And what we are going to do next is replicating the results from this paper. And remember that the variable of interest is the count of total protests. So we call this b hat 3. And we are going to estimate the negative binomial model, and we have to use the function glm.nb for negative binomial. Note that this is associated with the package mass. So again, we are putting the equation 1. We specify the data, which is BLM. And then we also have to specify what is called the link. And then we can summarize the data, b hat 3. And then note that here in this case we have the population density being back as statistically significant. Okay, and note that those coefficients are equal to the results in the original paper. Now note that the purpose of the paper was actually to see whether the number of black death caused by the police is actually increasing the number of total protests. So in this case, we are going to estimate the model, let's call this b hat 4, where we are looking at where we are including the per capita death of blacks caused by the police. So when we run this model, actually there is an S missing here, and there's also an S missing here. So when we run this model, okay, then we can see that the variable here is statistically significant. Okay, it is positive, which means that the number of protests increases if the city has experienced the death of blacks by police. Now, they have also tested whether it is true for the death caused by the police for everyone, so independent of race. So this would be the last model. And what you can see is that the police caused death, if you include the police caused death in general, that this is not statistically significant, but that it is statistically significant if you include the black police caused death. Okay, so those applications here and also those models can be used if you have count data. And the main important point here is that you have to be careful whether you have the mean and the variance are equal to each other. If that is the case, and you can test for that, you can use the Poisson model. Otherwise, you can use the quasi-Poisson model or the negative binomial model.